Hey guys, how you doing? I am going to go over 6.3 right now. Of course, you know you're going to do the definitions by yourself. All right, we're going to go over these problems right here. So the first one is right here on page 119. And this is about binomial random variables, of course. So as you see right here, here is the formula. Of course, we can do them on the calculator as well, though. Remember, with a binomial setting, there has to be 4 conditions that you find, and that's when we use that acronym BINS. B stands for binary, I stands for independence, N stands for set number of trials, and S stands for that every trial has the same probability. All right, and so right here, that's just kind of a brief explanation of all that right here. You have first, success or failure, that's binary. Next, you have observed trial of the random process must be independent of the other trials. That means what happens before doesn't have anything to do with what happens, after that. Third, the number of trials we observe must be fixed. And last, the success on each trial must be the same. All right, if conditions are met, use this formula, or you can go ahead and use the calculator, right, which is what we did in class often because it's a little bit of a confusing formula. All right, recall that there are 4 suits: spades, hearts, clubs, and diamonds, in a standard deck of playing cards. No problem. Right here, so suppose you play a game in which you draw a card. Record the suit, replace it, shuffle, and repeat until you have observed 10 cards. Define X as the number of hearts observed. Okay, so you're basically going to shuffle, and then this is with replacement. You're putting that card right back in the deck once you observe it. And then you do it again, and you're doing this a total of 10 times. So, show that X is a, a binomial random variable. No problem. All right, so first one, is it binary? Yes. In this case, success is going to be represented by having a heart, drawing a heart. And failure is not drawing a heart. Okay, independent. Yes. Okay. Drawing, it's first of all, it's with replacement. So drawing a heart before has no effect on whether you draw a heart currently. Okay. So you can just say what happens before does not affect drawing a heart. Sorry, this effect with an A, my fault. All right, no problem. Number, yes, there are a fixed number of trials right here. In this case, we have that N equals 10. All right, is the fixed number of trials. And lastly, right here is all the probabilities the same. Yes, drawing a heart. Okay, the same probability. Sorry. And drawing a heart is going to be 13 out of 52, which is actually 1/4. All right, if you want to reduce it to 1/4, up to you. Find the probability of observing fewer, part 2. Find the probability of observing fewer than 4 hearts in this game. Okay, so this is a binomial situation. Now, fewer than 4. That's the probability that X is less than 4. You know, and I always think a good way of doing this is looking at a number line. So less than 4, that could be 3 hearts, or 2 hearts, or 1 heart, or 0 hearts that you observe. So right here, remember, we have 2 options right here, binomial PDF or binomial CDF. CDF, if you recall, is less than or equal to, its cumulative. And that is what we are going to use right here, because essentially right here we have less than or equal to 3. So what we're going to use is we're going to use that the probability that x is less than or equal to 3. Okay, is what we're going to use. Remember what we have to do to show on the AP exam for when we're using our calculator. We're just going to say binomial CDF. All right. And right here, the number of trials, once again, we already said is 10. The probability of success right here, we already said right there, is 13 over 52, or you could even just say 1/4. And the x value right here for CDF, that's where it's going to be less than or equal to. So that, of course, right there is going to be 3. Okay, and if you want to map that out beforehand and just, write out and 10, P is 13 over 52. In this case right here, x is 3, 2, and 1. That way you know that it's, in this case, it's for the calculator, it's going to be 3. That's fine. All right, so then, of course, you're just going to put this into the calculator. We've done that in class many times. You should be okay with that. And you're going to end up with 0.7759. All right, so the probability that x is less than or equal to 3 equals 0.7759. This does not say interpret, but if it did, all right, this is an easy interpretation. The probability that you would observe fewer than 4 hearts, all right, when drawing right here 10 cards is 0.7759. Or you can say when drawing 10 cards with replacement is 0.7759. Okay? So let's take a look right here at the next one. The mean and standard deviation of a binomial distribution and the normal approximation. Some of this we've talked about, some of this we have not. So let's look through this right here. We have talked about the mean and standard deviation though. Like any other discrete random variables, we can calculate the mean and standard deviation of a binomial random variable. This will give us a better sense of what we'd expect to see in the long run, as well as how much variability we can expect to observe in the observed number of successes. If a random variable x has a binomial probability based on a random process with n trials, each having probability of success p, we can calculate the mean by n times p. So that's the expected value. The mean is n times p. We can calculate the standard deviation of x by taking the square root of the product of np times 1 minus p. Now, I always actually prefer to write this as just the square root of npq, where q is failure, and that's, of course, 1 minus p. Modified versions of these formulas are useful when trying to make inferences about the proportion of success in a population. If we take a simple random sample n from a population where n is less than 10% of the size of the population, then we can use a binomial distribution to model the number of successes in this sample. So we talked about that in class right here. If we know that if this passes the 10% rule, right, where n is less than 10% of the whole population, then we can use a binomial distribution to model the number of success in the sample. Furthermore, if n is so large that n times p and n times p times 1 minus p are at least 10, then right here we can use a normal distribution to approximate binomial probabilities. 1 second. All right, guys, one thing the reason I had just was confused is right here, as you know, in this book right here, there's sometimes mistakes in here in the workbook. I've noticed quite a few of them. All right, so NP is okay, but this is actually just going to be n times 1 minus p. Actually, that is a mistake right there. So it should be n times 1 minus p. And that's the normal approximation for the binomial distribution. We can use the normal distribution to allow binomial probabilities. As always, make sure you not only understand how to use the formulas, but also when to use them and how to interpret their results. Okay, no problem. So let's take a look right here. All right, show that suppose 72% of students in the U.S. would give their teacher a positive rating if asked to score their effectiveness. A survey is conducted in which 500 students are randomly selected and asked to rate their teachers. So just as I'm doing this problem, I'm going to say that right here, the probability of a positive rating is going to equal 0.72. And in this case right here, the n is going to be 500. Okay, let's continue on. Let X equal the number of students in the sample who would give their teacher a positive rating. So what we know is, since X is positive rating, we can say the probability of X, all right, happens to equal 0.72 right there. Show that X can be approximated by a normal distribution. All right, so right here, we know, first of all, a couple things right here. N times P, we have not done this in class yet. If N times P is greater than or equal to 10, and N times 1 minus P is also greater than or equal to 10, we can use a normal distribution instead of a binomial distribution to estimate this. And we actually, not can, we should actually. If it is greater than or equal to 10, we should. All right, so in this case right here, we know that, first of all, N is 500, P is 0.72, that's a probability of success. And when we do that, it's going to equal 360, that is greater than or equal to 10, check. Now we also know that right here, N is once again 500. 1 minus P is, of course, this going to be right here, 0.28. All right, and that's going to end up giving me 140, which is also greater than or equal to 10, check. All right, so we can right here approximate X with a normal distribution. Okay, next. Use the normal approximation to find the probability that 400 or more students would give their teacher a positive rating in this sample. So no problem. Okay, we want a probability that X would be greater than or equal to 400. Well, we have to figure out the mean and the standard deviation, don't we? Okay, so no problem. The mean of any binomial random variable is going to be N times P. So in this case right here, my N was, once again, let me just write that down so we can refer to it. N was 500. P was, once again, 0.72. Now, we already figured that out up here when we were doing the normal approximation. That came out to 360. All right, now the standard deviation is going to be the square root of N times P times Q. Remember, Q just equals 1 minus P. It's a probability of failure. So that's going to be right here. Well, we figured out that N is 500, P is 0.72, and Q is just 1 minus 0.72, which is 0.28. So when you do that in the calculator, you're going to get 10.04. Sorry if that's not dark enough. I'm going to rewrite that, 10.04. Okay, great. So we're going to go ahead and now make a normal distribution curve right here. So we know that our mean is right here at 360. All right. Standard deviation is 10.04. So right here, 360 plus 10.04 is 370.04. 360 minus 10.04 is going to end up being right here 349.96. Okay, no problem. Now we're trying to find the probability that X is greater or equal to 400. So 400 is something about right there, I guess. All right, and we're going to go ahead and shade that right there. So we'll just go ahead and say we can use the normal curve, right? So we're going to say normal CDF. All right, my lower is right there, 400. My upper is going to be 10,000. My mean is right there, 360. And my standard deviation is right here, which is 10.04. Okay, you put all this in, and you get, when you put this in the calculator, right, you have to go under VARs, don't forget. All right, just to remind everybody how to do that. Going in here. Okay, you press second VARs, there we go. And normal CDF is right there. Okay, don't forget. So you're putting everything in there, negative 10,000. Upper was 360. The mean is, I'm sorry, lower is 400. Sorry about that, guys. I was reading that wrong. Lower is 400. Upper is 10,000. The mean is 360. And the standard deviation is 10.04. There we go. All right, no problem. So we have it right there. And we're going to get a really small probability. This is this e to the negative fifth. That means 10 to the negative fifth. So that's going to be 0.0000338. Okay, so basically, essentially, this is 0. So the probability, all right, that 400 or more students would give their teacher a positive rating is essentially about 0, okay? Or exactly 0.0000338. You know, actually, that's approximating 2 because it's a, you know, it's a decimal that never ends, okay? All right, so that is there, okay? Let's go to the third one right here. Now we're on geometric random variables. All right, in a binomial setting, we're interested in knowing how many successes will occur in a fixed number of trials. Sometimes we're interested in knowing how long it will take to until a success occurs. So geometric is basically you keep on going till you have that success and then you stop. When you perform independent trials of a random process with the same probability of success on each trial and record how long it takes to get a success, we have a geometric setting. We can describe the number of trials it takes to get a success using a geometric random variable. As with other random variables, we can try the probability distribution of a geometric random variable and calculate its mean and standard deviation. Using that, what we learned in Chapter 5, we can calculate the probability of observing the first success on the kth trial by multiplying the probabilities k-1 consecutive errors by the probability of success. All right, I'll tell you what they mean by that in a second. But what they mean is basically, instead of using the geometric random variable, you can just think right here, you know, the probability of success, well, it's just going to be, if you have like 5 trials, well, you have basically 4 failures, q times q times q times q, and then 1 success, p. So it'd be what? Q to the 4th times p. All right, so that's where the formula comes from. So right here, suppose 20% of SuperCrunch cereal boxes contain a secret decoder ring. X is the number of boxes of SuperCrunch that must be opened until a ring is found. Show that X is a geometric random variable. Now, right here to show this, you're going to do the same thing as binomial, except you don't have that n. You don't have a set number of trials. So right here, is it binary? Yes. Okay. In this case, of course, it's binary, right? You have 2 outcomes. Either you get the ring or you don't. All right, independence. Yes, right here. All right, getting a ring right here at one point does not mean that you're going to get a ring at the next point, okay? So just say what happens before does not affect getting a ring. And then right here, S is the same probability. So right here, the probability of a decoder ring, it's all the same right here. That's just going to be 0.20, okay? No problem. Find the probability that you will have to open 7 boxes to find a ring. All right, so you could do this by hand or the calculator. If you're doing it by hand, just think about that. That's going to be right here, 7 boxes. That means the first 6 will be failures, and then the last one will be a success. So the probability of not getting a decoder ring is going to equal 0.80. So that would be what? If it's 7 boxes, that would be 0.80 to the 6th power times 0.20 to the first, or just 0.20. You could just do that by hand right there. Okay, so you would get right there, just doing that, that would be 0.80 to the 6th power, and then right here times 0.20 to the first, and you'll get 0.0524, right? Now, if you want to just continue, if you're comfortable just doing all of these on the calculator, you could do that way also. This would be geometric PDF, right? Because it's just one specific instance, open just 7 boxes, right? Now, right here, in this case right here, we don't have a set number of trials. So all that's going to be here is your probability of success, which is 0.20, and your X value, right? That's how many boxes you want to open up. In this case, it's 7, right? So it would just be 0.20 times 7, and you would do the same thing. You're just going to go to second vars, go over here to geometric PDF. There it is. And right here you have 0.204p, and the X value is 7. There we go. All right, so we have it 0.05. See, we get the same answer. So you can do it either way. Now, find the probability it will take fewer than 4 boxes to find a ring. Doing this by hand would be a little harder because you'd have to get the probability of 3 boxes, plus the probability of 2, plus the probability that it's going to take 1. Now, actually, I incorrectly have 0 right there because remember, it's geometric. It's all about getting a success. So 0 is not part of this at all. So, but what this is going to be, if you're using our calculator right here, you're just going to say right here that right here we're doing the probability that X is less than or equal to 3. Okay. All right. So we're going to say geometric CDF. All right. And my probability of success is once again 0.20. My X value, right? We're talking about right here 3, 2, or 1. Okay, so the CDF, that means less than or equal. We're going to use X value is right here, 3. All right, so there we go. All right, so we put that all in. We're just going to go second vars, excuse me, and geometric CDF is right there. All right, it's 0.2, and the X value is right there, 3. And right here, it's 0.488 is what we get right here, okay? So yes, 0.20, and the X value is 3, geometric CDF, and you get 0.488. Let me just check this again right here just to make sure, because I got something different before, but geometric CDF, yeah, 0.20 is the probability, the X value is 3. No, that's it. Okay. All right, so yeah, it ends up being 0.488. Okay. There we go. Okay. How many boxes would you expect to have to open to find a ring? All right, so what we're going to do right here, that's your expected value for geometric. No problem. Your expected value, which is just going to be your mean, right? So let's take a look on this formula sheet right here, which is in Google Classroom, right under, right there, formula sheet. We'll get the formula for expected value right there of geometric. Here we go, geometric. It looks like the mean right there is 1 over p. So we're going to go ahead and use that right there, okay? In this case, p is 0.2, so 1 over 0.2. And we get right here 5. So that's going to be 5 boxes, okay? All right, and if you're interpreting this, remember over many trials right here, we're going to say over many trials to get Supercron serial box decoder ring. It will typically, you can expect or typically take 5 boxes to get a actual ring, okay? Or you can even say it'll take an average of 5 boxes to get a ring. Right here, what's the standard deviation? The number of boxes you expect to open to find a ring. Now we're going to have to interpret this one. All right, so the standard deviation is right here. That's going to be square root of 1 minus p all over p. So let's do it. Okay, it's going to be square root of 1 minus 0.2 all over 0.2. All right, when you figure that out, that's going to be 4.472. So, all right, we're going to interpret that. If many serial boxes were opened, the typical number of boxes opened to find a ring would vary I'm going to put about 4.472 boxes from the mean of 5 boxes. There we go. Okay. So it's just a script that you're always following right here for standard deviation and mean. Mean is obviously your average, and your standard deviation is your typical distance from the mean. Okay. All right, guys, have a good day. See ya.